Hi, my name is Manish Gupta, and in this video, I'm going to talk about XR Transformer, which is a way of doing fast multi-resolution transformer fine-tuning for extreme classification. Okay, so you'll try to understand every word in this phrase. How it is fast, how it incorporates multi-resolution fine-tuning of transformers. Right. So recall that extreme classification is the problem where you want to do multi-label classification in the space of millions of labels, right? So let me start with a broad idea of how XR transformer training happens, and then essentially we will delve deeper into the details. Okay. So very broadly, right? We have studied several kinds of different ways of fine-tuning models for extreme classification. So one of the simplest ways is to do one versus all transformer classifier, build one versus all transformer classifier in the space of original set of labels. Now that's the dumbest thing to do, or that's basically the simplest thing to do if you are not careful about efficiency at all, right? So and why is it really inefficient? It is inefficient because the number of labels are too many. Okay, so it's going to give you slow fine tuning, but it gives you high label resolution, right? So you're basically fine tuning in the space of the original set of millions of labels. So it is slow, but accuracy wise, of course, it could be pretty good. Okay. The other extreme way of training this is to essentially do no fine tuning, which basically means it'll be super fast because you're not doing anything. And then the idea is that, well, there's no fine tuning at all. Okay. Now, last time I talked about light XML. So in light XML, actually, you do something in between. Essentially, you build a parallel tree and then you sort of solve a meta XC problem in some ways. Or other, you sort of use, you don't solve a meta XC problem, but you use the clusters which are available at let's say 2-layer or 3-layer deep in a parallel tree. Okay, so it is a hierarchical tree in the space of labels. Okay. Now, what XR transformer says is that it is actually in some ways very similar to attention XML. Attention XML also does this it basically builds a parallel tree and then it does meta XC problem solving at different levels of the parallel tree. Okay. So XR transformer is similar. However, unlike attention XML, which sort of tries to learn a model per level of the tree, XR transformer basically just uses the same transformer encoder. It sort of learns transformer encoder or other, it sort of learns the entire classifier along with the transformer encoder for the first level of the tree, then for the second level, then for the third level, then for the fourth level. So it sort of solves the same meta-XC problems as attention XML, but rather than retaining copies of the model at every level, it keeps refining the same old model. Okay, same model. Yeah. Now that's the broad idea of XR transformer training. Now there are more tweaks to it, and we'll discuss those tweaks one by one. Right. So by actually not starting the training at every level from scratch, it basically accelerates this XC level training, right? And as you already understood, like attention XML, it has multi-resolution objectives related to the original XMC, original XC problem, extreme multi-label classification problem. Okay. It also does recursive fine-tuning of the transformer encoders, right? So essentially, rather than doing it, um, you know, in one go or starting from scratch per level, it sort of does recursively fine-tuning of transformer encoders. Okay. Now, what is the kind of embedding that you can use for the data points is the question. So mostly people have basically used typical TF-IDF based representation for your data points. The other way of doing this is to also learn these embeddings on the go as you do training. Okay. And that is what basically leads to the training procedure, overall training procedure of the XR transformers, which is shown on the left side at the bottom. Okay. So you start with the data points and you first follow the blue path. So basically, you first compute the TF-IDF vector representation of the data points. That's all you can do, right? I mean, in the beginning, that's all you have, right? So you use this representation so as to train the transformer encoder at the first level. Remember, you of course build a parallel tree. So on the parallel tree, first level, you essentially train your representations at the first level. We'll call those, trained model as W hat one. Then you train at the second level, you train at the third level, you train at the fourth level. You keep training, right? You keep training. So that's basically your training step one. So your training step one, you're done. Okay. Now, once you are done, you essentially feed back these information so as to essentially, feedback in the sense this information has helped you train the embedding part of your model. So the embedding, I mean, we'll call that as phi DNN. So the TF-IDF representation is just phi TF-IDF, but then embedding part is phi DNN. So after you come up with the embedding part, embedding for each data point nicely, you can actually concatenate these embeddings. So concatenate phi DNN and phi TF-IDF, of course, with appropriate normalization and so on. And that gives you your new embedding representation for every data point, which is basically a syntactic plus semantic representation. Why? Because, well, TF-IDF supplies the syntactic representation and phi DNN supplies the the semantic representation. And after you get that, you repeat the same story. So in the sense that you essentially again train the refined HLT. HLT here stands for the hierarchical label tree, right? So the parable kind of a tree, hierarchical label tree. Okay. So essentially you fine tune again, starting from W1. So first level, second level, third level, fourth level. And then once you're done, you basically have these different Ws classifiers at different levels. Okay, so that's that. Now, of course, so the training essentially consists of 3 steps. One, you do this blue stuff. Second, you do the red stuff. And third, you do this violet stuff that is shown there. Okay, that's that. Now, at inference time, of course, you can throw away this preliminary HLT. You don't really need that, right? So essentially, all you need is phi DNN, which has been trained using that original, that first level. Okay. And then you, of course, need phi TF-IDF. Given a new data point, you'll compute both of those embeddings using those 2 models. I mean, phi TF-IDF is not really a model, but phi DNN is surely a model, right? With parameters theta, right? So you're going to concatenate those embeddings, and then you get the phi cat, and which is what you're going to use with your refined HLT so as to come up with appropriate predictions at inference time. Okay? So that's a broad idea. Now let's look at through the equations and sort of try to understand more details of this idea. Okay. So in some ways, because XRTransformer is sort of training from the top of the tree right to the bottom, right? So it's sort of solving a simpler XE problem at the top because you have less number of labels to care for, and then progressively you keep going to harder and harder problems to be solved, and that is what is popularly called as curriculum learning. So you solve easy problems first, and then you solve harder problems. Okay. So you fine tune the pre-trained transformers progressively on sub-XC problems, sub-XMC problems with increasing output space, right? So at the top of the tree, your number of labels are probably like just B, and then second level it becomes B square, and then third level becomes B cubed, and so on. Okay. So that's that. So now at each fine-tuning task, the candidate label set is shortlisted by the final model at the previous task, right? So remember, when you're solving these sub-XMC problems, at every point, there is it's after all XC problem. So, the label space can be very large. In the beginning, it's sort of small b square, b cubed may also be small, but then b raised to 4 could be very large, right? So when you're doing this, basically you're trying to again solve a XC problem, and to solve it efficiently, you need shortlist. By shortlist, I mean you cannot really train every data point on all the set of labels. You have to basically shortlist a few positive and a few negative labels. So positive labels, because you can sort of map your positive labels to those meta clusters in that senses by propagating that label from the leaf nodes to those meta clusters by saying that a meta cluster is basically positive for a data point or relevant to a data point. If it contains at least one label, if its subtree contains at least one label which is positive, right, which is relevant. Okay, so essentially, but then, how do you figure out the shortlist? So at each fine-tuning task, or each level, the candidate label is shortlisted by the final model at the previous task. So remember, you trained a final model for the previous level in the tree. You trained a model there, right? So that model comes up with predictions for every data point that, hey, which of those nodes are sort of relevant for this particular data point. You make use of those scores so as to decide what should be the shortlist for your next level task. Okay, so that's that. So that's for the shortlisting, and also for embedding. You use the embedding generated at the previous task to bootstrap the non-pre-trained part for the current task. Okay. So remember, for every task, there is a pre-trained part and there's a non-pre-trained part. Pre-trained part is for the embedding of the data points, and non-pre-trained part is for the weights in the layer, right? Weights in the final classifier layer. So for the pre-trained part, of course, you keep using the same transformer. So that's that, right? So basically, you just do transfer learning from the from the previous task to the next task in that senses. Okay. But for the non-pre-trained part, you essentially just take those Ws which have been sort of trained in the previous task, and you try to use those so as to initialize the Ws for the next task. Okay. So basically that's that. And then, I mean, as I mentioned, you do recursive shortlisting. So for any level, the number of candidate labels in training has to be, or even an inference has to be O of B. It cannot really be O of L, right? So of B is very, very smaller than L. B is much, much smaller than L, which basically means the overall number of labels that you will care for is going to be B log L, because you'll be solving, log L different XMC problems. Okay. Both at training as well as at inference time. Okay, so that's that. So now let's get into even more details, right? So that was the next level, and now the deepest level of details with all the formula and so on. Okay, so the first step, always build a HLT, right? So essentially in XR transformers, it is a tree-based method with deep learning. So essentially build a HLT, hierarchical label tree, and the way you do that in the beginning is by basically saying that, hey, I have a representation for my labels, which is a unit vector, right? So you have normalized that. And what is VL? VL is basically just an aggregation of the features related to the data points which are relevant, for which this label is relevant. Okay? So you have a label, you try to figure out data points which are for which this label is relevant. For those data points, get the TF-IDF vector representation, or some other representation like DNN representation that you'll have later. And then you sort of take the sum, and that's basically your VL. That's basically your representation for the label. Okay. Of course, you normalize it, so essentially that gives you a unit vector for the label. And then once you have these unit vectors for the label, you essentially, this is also called as positive instance feature aggregation. You just, aggregating features across positive instances related to this label. Okay. And then you do balanced k-means with the k equal to b. So in this paper, they don't choose k equal to 2, they choose k equal to b. And essentially that gives you a whole bunch of clusters at different levels. Okay. So in fact, as output of this balanced k-means, what you get is a cluster hierarchy. So essentially what you get is at every level, you have a mapping from this level to the next level. So if at level T, the number of clusters is KT, and level T minus 1, the number of clusters is KT minus 1. You have a cluster mapping matrix, which basically says that is this cluster, a child of the other cluster or not? Is this cluster a child of the other cluster or of the parent cluster or not, right? So that's basically your CT. So you have like CT from C1 to CD, where D is the overall depth of your entire tree. Okay. So that's that. So that's how the tree is made, right? And the tree is basically indicated by the capital C. Okay, so that's that. Now, multi-resolution output space. So the idea is that you have to map for every level what are positive data points, right? And to be able to do that, the way you do that is as follows. You could basically just take the lowest level, where the idea is that at the lowest level, of course, every leaf is just one data point, one label, and for a given data point, which leaves are essentially relevant. Now you could propagate those labels right to the top, and then say that, hey, the parent nodes of these leaves, for relevant, any internal node is basically relevant if it contains, if its subtree basically contains even one leaf, which is relevant to the entire, to the data point, right? However, this could mean that certain nodes may contain, even if they contain, let's say 100 labels, but only one of them is relevant, you will still call the node as relevant, which is basically a problem. Or rather, it's not as relevant as another node, which basically contains like 90 different labels out of 100, which are relevant to the data point. Okay. So there should be a notion of segregating those internal nodes which are more relevant to the label to the data point compared to less relevant to the data point. Okay. So therefore, the way to solve this problem is by actually is by actually giving partial credits. So basically, the idea is to say that rather than just doing binarization and essentially giving a label of relevant or not to every data point, they're actually going to give a scores. So rather than actually saying that it is completely relevant, they're actually going to give scores. Okay, these scores are indicated as R. Okay, and now of course at every level you have n data points and KT different clusters, right? So you have scores for each of those clusters for each of those data points. That makes sense, right? Now, you're going to, of course, compute your, you're sort of going to aggregate the label at every level, right, at every level based on the labels at the underneath level. Okay, so essentially, you're going to take your RT plus 1, which is the labeling for the children level, right? And you're going to basically use the same clustering representations as to get the representations for or the labels for the higher for the parent level. Okay. Of course, the base case is just that. I mean, essentially, you initialize your leaves with the relevance labels which are already known in the original training data. Okay. So D is the depth. D is the depth of the overall HLT, right? So now the important stuff is here, right? So at every level, after you have done this step, you have basically borrowed the information from the child level. You basically normalize, okay? And this normalization is interesting because that basically tells you that out of the entire set, right? Out of the entire set at the same level, how important this particular cluster is. Okay, so that's basically that. They also have a hyperparameter alpha here, so as to essentially give some non-zero weight even to non-relevant nodes, non-zero weight to non-relevant nodes. So the idea is that it has multi-resolution output space, but then the output space is not just binary. It is basically formed in a way such that you give appropriate scores, giving higher weights to those clusters or those nodes, which basically are more relevant or rather relate with more relevant labels compared to less relevant ones. Okay, so that's that. Now, the next step is label shortlisting. So at any layer T, at any label T or layer T, the labels considered during training are shortlisted by the parent layer. That makes sense, right? So first of all, why do we need shortlisting? We need shortlisting because at any point, you cannot really use the entire label set to train for a given data point. Even for inference, you cannot really make use of all the labels at that level. Okay? So therefore, you need to do shortlisting. Now, to do shortlisting, a simple method could be just to use the ground truth labels. You could just do that, right? You could basically say that, hey, let me use the ground truth labels at train time, take all the positive ones for the negative ones. Well, let me just randomly sample from the entire set. Big deal. Okay. But it turns out that that does not work, right? So because there is a train test mismatch at inference time, you're basically just going to take, those that are going to be predicted as really relevant at any level, right? So therefore, for a good train test match, the way they do that, they do the shortlisting is as follows. Shortlisting combines two things. One, it depends on the ground truth labels at the level at layer T minus one. So at layer T minus one, they basically take the ground truth cluster nodes and then take its children at the layer T, and they take all the labels which are, or rather all the children at layer T. Okay, so those are basically, of course, considered in the shortlist. But they also do another interesting thing. At layer T minus one, you've already trained your Ws. So you already know the classifier. This W is the classifier at layer T minus one. So you already know the classifier at T minus one. And you also know of course, the embedding representation for a data point X at layer T minus one. You use that so as to figure out what are the top K nodes that are relevant at layer T minus one for the current data point. Okay? We call them as PT minus one. And basically what you do is to essentially take all the children of PT minus one at layer T, and that's what you're going to use as your shortlist. So your shortlist is going to be a combination of the labels predicted by the parent at layer T minus one, and also the real and also the actual labels as predicted by the as given in the training data in that senses. Okay. So that's that. So essentially, you use this shortlist set M, and that's what you're going to use so as to train the classifier W and also the embedding parameters theta at any layer T. Okay, so that's how overall training happens. That's the basic. That's basically XRTransformer training. Okay. Now, the important part is that text representation, as I mentioned earlier, XRTransformer basically uses two different text representations. One is essentially the TF-IDF representation. The other is the learned deep neural network based representation. Okay. So, of course, it's learned over every layer. Every layer theta, right? So, and it's updated at every layer. So there's a statistical feature representation, TF-IDF based, and there's also semantic feature representation, deep neural network based. Okay. So again, to repeat, the training happens with bootstrapping in multiple steps, prominently 3 steps actually. The first step is construct the hierarchical label tree using TF-IDF features. Okay. Fine-tune the pre-trained transformer recursively from low to high resolution outputs. You start from the problems at the top level, and you sort of progressively keep refining until you reach the bottommost level, right? And solve the overall axis problem that you started with. Okay. At each layer, you initialize your theta, the embedding parameters, with the best transformer weights of the layer t minus 1. Okay, so basically, you just solved the problem at t minus 1. Just use that to initialize the embedding parameters at layer t. And also, the W's have to be initialized wisely by leveraging the recursive learning structure from the previous layer. Okay. So that's that. So now how does XRTransformer perform? Well, I mean, comparison with the several data sets, I've just shown 3 here, but they compare in the paper with 6 different data sets across different methods here, deep learning as well as non-deep learning methods. You see that, XRTransformer actually performs really well. Okay. So, XRTransformer is closest to attention XML. In attention XML, you basically build LSTMs at different level and you keep all of them. So final model is therefore a chain of multiple submodels. Unlike that, in XRTransformer, basically you just keep one model at the end. I mean, well, you basically have an ensemble, but then the idea is you don't keep a model per layer. You basically keep one model per label tree. Okay, and then you can basically build like 3 different models like BERT, robot, AxleNet, transformer encoders, and that's how you see that the results for XRTransformer are the best, right? Now they also basically experimented with different ensembles, different number of models in the ensemble, 3, 9, and so on. And what you observe, and they noted the training time. So what you observe is that XRTransformer gives you really good accuracies, but also with very low training time compared to other methods like attention XML, light XML, and so on. Okay. So that's it for this video. In summary, in this video, I talked about XRTransformer, which is a method for accelerating XC training, extreme classification training. It uses recursive fine-tuning of transformer encoders and also uses multi-resolution objectives related to the original XC problem. Okay. If you want to play around with the code is there. Also, hope you like the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.